Hello, let us introduce in this video the technique of evaluating the error involved in calculating the numerical integration with the three formulas: trapezoidal, Simpson, orbital. We will focus on trapezoidal rule. Which we all know this is obtained from the quadrature formula of a to b fx dx by putting n equal to 2. That means we are subdividing this interval a to b by two sets of points, x0, x1, then x1, x2, then x2, x3, then xn minus 1 xn, and summing them up we get this type of formula: x1 plus x2 plus x3 plus dot 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 xn minus 1 plus xn. This is the trapezoidal rule, we all know, where the endpoints are multiplied with coefficient 1 and all the other nodes are multiplied with 2. This is simply because we put n equal to 2 in the general quadrature formula and evaluate this interval term by term. Now we would like to evaluate the error involved in calculating the value of the interval through this numerical formula, numerical technique rather. So to find out the error involved, actually we would like to embark upon the fact that if we integrate any function fx dx, say from x0 to x1, we know that this x1 may be replaced as x0 plus h fx dx. Isn't it so? Now, what is fx at this point? We may write it with the help of what we know as Taylor's theorem. Isn't it so? We all know that f of x0 plus h, which is nothing but f of x1, may be written as f of x0 plus h of f prime x0 plus h square by factorial to f double prime x0 and so on. We know this Taylor series expansion of fx at this node. Now if we replace this value of fx in terms of this expression, where we actually tend to put x1 minus x0 is equal to h. And then, as we know that the value of this integral according to trapezoidal rule is nothing but this, isn't it so? From trapezoidal rule we know, by putting n equal to 2 in the quadrature formula, that this becomes this, y0 plus y1 by 2. And what is y1? Actually this is nothing but y1. So with this expansion, this may be written as y0 plus hy0 prime plus h square by factorial 2 y0 double prime dot dot dot. So if we substitute this value of y0 here, we may easily find that the value of I turns out to be, we are just replacing y1 by this. So what does it become? It becomes y0 by 2 plus half of this y1, which is nothing but y0 plus hy0 prime plus h square by factorial 2 y0 double prime plus dot 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 this. And hence we may have the value of this integral according to trapezoidal rule turning out to be y0 by 2 plus y0 by 2 is y0 plus h by 2 y0 prime plus h square by 4 y0 double prime and so on. So this is our numerical approximation of the integral a to b fx dx. Now let us calculate the same with the help of this Taylor's series expansion, replacing as in the actual integral. What is our actual integral? Our actual integral is nothing but a to b fx dx, isn't it so? So we tend to write it as, since we are concerned with the 2 points x0 and x1, obviously we substitute x0 and x1 in place of a and b, because we know that we can subdivide this a to b in this format. This is the general technique we all know. So we are primarily interested in this integral only. Now just replace this fx by the formula which Taylor series gives us. Then what it becomes? It becomes nothing but fx0 plus x minus x0 f prime x0 plus x minus x0 whole square by factorial 2 f double prime x0, and we don't write any terms beyond these square term for reasons quite familiar to you. Whenever we tend to evaluate the error involved, since we are concerned in trapezoidal rule, we tend to ignore the values beyond h square, simply because h cube, h to the power 4 and higher orders are negligible, h being very small. So we tend to evaluate the error to the tune of square term of h. Now what is the value of this integral? Here we have replaced fx by its actual expansion around the point x0. So the increment is assumed to be x minus x0. Then if we integrate it term by term, just see what is the first term. First term is fx0 dx. So it becomes fx0 into x1 minus x0. Isn't it so? Since fx0 is constant, it comes to the left hand side of the integral, and when dx is integrated from x1 to x0, it becomes fx0 into x1 minus x0. I just want to repeat at this point actually what we are going to do. We are trying to evaluate the error involved in approximating integral a to b fx dx by the trapezoidal rule. In trapezoidal rule, we know that we replace the general quadrature formula by n equal to 2. That means we divide the interval by 2 nodal points, and the formula turns out to be y1 plus y0 by 2 in case of the first interval, and we have replaced that y1 by the Taylor series expansion with respect to y0 with the step length h, and then the numerical formula turns out to be this. Now we tend to evaluate the actual integral x0 to x1 fx dx, where we replace fx by the Taylor's expansion with the approximating point x, which is very near to x0. So we are calculating the actual integral. This is the actual integral term by term. So what is the first term? Fx0 dx. It becomes fx0 x1 minus x0. Now I am wiping it out and just remember this formula. Just remember this formula. This formula is the, I am writing it here, I equal to y0 plus h by 2 y0 prime plus h square by 4 y0 double prime, and so on. This is the trapezoidal rule formula. And now we would like to calculate this term by term. So the first term is fx0 into x1 minus x0. What about the second term? Second term is this. So f prime x0 is actually constant, and it comes out of the integral sign. Now what is the value of the integral x0 to x1 x minus x0 dx? It is x square by 2 minus x0x, and the limit of x runs from x0 to x1. Clear? If we integrate this, it becomes x square by 2 minus this. What about the second term? The second term, f double prime x0, comes out of the integral sign being constant, and then we tend to integrate this term, which is x square minus 2x x0 plus x0 square. So when we integrate x square, we have, just remember that there is a factorial 2, so we should not forget about this. I write it as half. So x square when integrated gives x cube by 3, the first term of this. The second term is 2x x0. When x is integrated, it gives x square by 2. So this term, 2ab term, becomes x square x0. I think it is clear. And the last term is plus of x0 square dx. So when integrated, it gives x square x. So this is the three terms which we have integrated. And I will just evaluate these three terms. Okay. So what is the value of integral x0 to x1 fx dx, where we have replaced this fx by its Taylor's series expansion with respect to, this is actually x0 to x1 fx dx, where we have replaced fx with its Taylor series expansion with respect to a point near to x0, which is x, running coordinate. And these three terms we have taken. First one is fx0 times x1 minus x0, next one is f prime x0, and if we put the value here, this is actually h, so we can write, and this is actually y0, isn't it so? This is actually h y0, simple, plus what about this? This is y0 prime, and when we put these values, this becomes x1 square minus x0 square by 2 minus x0 x1 plus x0 square, isn't it so? Because first you put x1 here, x1 square by 2, and then you put x0 here, x0 square by 2, so it becomes x1 square minus x0 square by 2, and when you put x1 here, it is minus x0 x1, and when you put x0 in place of x here, it becomes minus of minus, which is plus x0 square. Now we take x0 common from these two terms, so what does it become? It becomes x1 minus x0, isn't it so? And here it becomes x1 plus x0 by 2. So if you calculate a simple algebra, it becomes nothing but, let me do it with blue ink and then wipe it out. Let me do it in blue ink, this calculation. It is clear that if we take x1 minus x0 common, then it becomes x1 plus x0 by 2 minus x0. Isn't it so? Just see, this is x1 plus x0 into x1 minus x0. I have taken minus x0 common from these two terms. So there is x1 minus x0, and you take this x1 minus x0 from these two terms common out of the bracket. So in the first place we have x1 plus x0 by 2, and in the second place we have minus x0. And what is the result of this? It is nothing but x1 minus x0. So actually this term is evaluated as x1 minus x0 square by 2. Okay, so we can replace this term with h square by 2. That is this term. Next we calculate this term. And what is this term? This term becomes, just see that this is y0 double prime by 2. And whenever we put these limits here, it becomes x1 cube minus x0 cube by 3 minus x1 square x0 plus x0 square x1. That is when we put x1 in place of x here and in place of x here. Then we put x0 in place of x here and in place of x here, and it is subtracted, so it becomes plus of x0 cube. If we put x0 in place of x, it becomes plus of x0 cube, and this is minus of x0 cube. So these two terms cancels out, and we have left with these two terms only. Okay, now we again should take x0 x1 common, minus x0 x1 common from these two terms, isn't it so? So if you take minus x0 x1 common from these two terms, it becomes x1 minus x0. It's quite clear. And then if we do a little algebra, we know that x1 cube minus x0 cube is nothing but x1 minus x0 into, this is nothing but, if we do a bit algebra, this is nothing but x1 minus x0 into x1 square plus x1 x0 plus x0 square by 3, and we have minus x0 x1 what here. If we obviously take the x1 minus x0 term common to the left hand side, and if you do this algebra, this becomes x1 square plus x1 x0 plus x0 square minus 3x0 x1, which is actually x1 square minus 2x0 x1 plus x0 square by 3, which is nothing but x1 minus x0 whole square by 3. So this is actually nothing but x1 minus x0. This is actually nothing but x1 minus x0 whole cube by 3. Since x1 minus x0 is taken common outside, and what we are left with? We are left with x1 minus x0 whole square by 3. So when multiplied, we have x1 minus x0 whole cube by 3. And we can replace this term as here, in place of this, we have plus of y0 double prime by, there is a 2 and there is a 3, so it is 6. The value of this term is actually nothing but h cube, isn't it so? So this term is like this. So this is the value of actual integral, and the value of the numerical integral is this into h. We all know this into h. Since this is y0 plus y1, you should remember, I am writing it again. We have here as the value of this integral I, when we use trapezoidal rule, it is nothing but y1 plus y0 by 2 into h. And what is y1? y1 is nothing but y0 plus h y0 prime plus h square by factorial 2 y0 double prime and all that divided by 2 into h. So it becomes h into what we have earlier calculated. It becomes h into y0 by 2 plus y0 by 2 plus h by 2 y0 prime. Let us write it by multiplying this h with this, and we have h y0 plus h square by 2 y0 prime plus h cube by 4 y0 double prime and so on. So this is the actual value and this is the numerical value. So what is the error involved? If we subtract this from this, we see that these two cancels out, and this term is actually nothing but, this term is actually nothing but h cube by 4 minus h cube by 6. So we have the error term calculated as, the error term is h cube by 6 minus h cube by 4 y0 double prime and which is equivalent to actually h cube by 12 with a minus involved here, because this is what we got when a to b fx dx. From a to b fx dx, we take the difference of I according to the trapezoidal formula, and we replace here a to b by x0 to x1, and in this calculation we have ignored all higher powers of h. Isn't it so? So that is precisely the technique how we tend to evaluate the error involved in numerical integration. You can do the same when you use the so-called Simpson's 1/3 rule. We all know that in case of Simpson's 1/3 rule, we put n equal to 3, and in that case we can similarly find out the error involved in replacing this a to b fx dx with the Simpson's 1/3 rule, which actually is nothing but h by 3 y0 plus 2 into y1 plus y3 plus dot 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 all the odd terms plus, sorry, this is 4 into, this is